So I have already sent you this particular sheet through your class representative. So have you received this, everyone? So title of the experiment is calibration of ammeter voltmeter. So here we have defined that what is calibration. Somebody is raising his hand. I don't know why. Okay. So calibration of ammeter and calibration of voltmeter. Calibration means basically the comparison between two instruments. Okay. Now, when we are going for ammeter calibration, we'll take two ammeters. One will be standard, another will be test. Okay. With respect to the standard ammeter, we'll check whether there is any error, or if there is any error, then we will map it for all the readings. Okay, suppose the ammeter is 0 to 10 ampere. Now for all this scale, that means 1 ampere, 2 ampere, 3 ampere, up to 10 ampere. For all these readings, we'll check how much error it shows with respect to the test ammeter. Okay, so this is how we calibrate the ammeter, and same we do for the voltmeter as well. So have you read this? Have you read this sheet? Okay. So if you don't, then so this is the circuit diagram. The first one is the circuit diagram for the ammeter calibration. Here you can see that two ammeter will be used. The test ammeter, which we are going to calibrate with respect to a standard ammeter. For our laboratory, both the ammeters are same, but when we'll bring two ammeters from the instrument issuing room, so we'll mark one ammeter as a standard ammeter, another ammeter as a test ammeter. Okay, only to learn how to calibrate. Now, once you have these two ammeters, almost similar range, you have to connect these two ammeter in series as given in the figure. Also, you have to connect two rheostat, rather two resistances in series. Exact connection I will show you in some videos. And then the series combination of all these four elements, that means two resistances and two ammeters, will connect the series combination of all these four elements across a 110 volt DC supply, which is available in our laboratory. Okay, so this is the connection diagram for ammeter calibration. Similarly, when we do the voltmeter calibration, we take two voltmeters from the instrument issuing room. One of the voltmeter we mark as a standard voltmeter, Another voltmeter we mark as a test voltmeter. Okay, now this both the voltmeters we connect in parallel. So that is the difference with the ammeter calibration. Okay, generally voltmeter measures the voltage. Voltage is an across parameter. So it generally the voltmeters are connected in parallel. Now this parallel combination of these two voltmeters then connected with a rheostat. So you can see there are two rheostats in figure 1a as well as in 1b. Can you tell me the difference? What is the difference? The symbol of rheostat, all I think you can recollect the symbol of rheostat. But what is the difference of their application in these two cases? Can anybody tell me? কেউ বলতে
So like
পারবে?
the question is such that why in the
Sir, in the second case, it can be shorted in 1B.
No. Okay. Any other difference? It can be sorted. But both the cases it can be sorted. Okay. So the inverse cases, I think you have seen the rheostat in our lab, no? When you
yes sir.
okay.
Yes, sir.
Now, how many terminals a rheostat has? Can you recollect?
Sir, 3.
Three terminals. What are the three terminals?
So one was the variable terminal and the other two was like the fixed one.
Is it so?
Maybe
No,
I'm not sure.
it's just opposite. Okay, so two terminals are fixed terminal and one terminal is the variable terminal. Okay, I think I don't have that video, then I will show you that. Just a minute. I'm just finding where. So anyway, I don't have that video right now, but I can show you that by some diagram. So as you can see from this diagram that the fixed two ends are these two ends. Okay, so this is one fixed end and this is one fixed end. Now in the first diagram, that means the diagram 1a, one fixed end is connected, another variable is connected. That means only two terminals of the rheostats are in use. Another terminal is open. So this type of configuration is called the variable resistance mode. Here you are using the rheostat for giving a variable resistance. Okay, but in the second case, that means in the figure 1b, all the three terminals, that means the both the fixed terminals and the variable terminals are in use, isn't it? So that means Here what you are doing, fixed to terminals, you are connecting, just follow the circuits carefully. The fixed to terminals, you are directly connecting across the supply, 110-volt supply, as given in the figure. So fixed to terminals of the rheostat directly connected across the supply. And the variable terminal is connected across the voltmeter. Now in this way, what you will get, you will get a variable voltage at the output. So input is the fixed voltage where you have the fixed two terminals are connected, and at the output you will get the variable voltage. Okay, so this type of configuration of rheostat is called the potential divider mode. Are you getting? So in the first case, we have this and this. So these two ends are the fixed ends. And this is called the variable ends. Okay. Now, if we connect this to the source, okay, and this variable to the source, that means what we are doing, actually this length we are varying. And we know that the resistance is nothing but rho L by A. So thereby we are varying this length, thereby we are varying the resistance. Okay, so it's called the variable resistance mode. And in the second case, what we are doing? We are having the same voltage source. It can be 110 volt DC. And we are directly connecting the fixed two ends. These are the fixed two ends. The fixed two ends directly we are connecting across the supply. And we are taking the output from these two. So here we have the output. Okay. Now you know that this output voltage will vary, and that depends on the where we have this pointer. Okay, so this is called the voltage dividing rule. Suppose this total is L, capital L, and this length is small l. Now what will be the V0? Can anybody tell me? It's very easy. That needs the concept of your 10+2 standard only. It's a voltage dividing rule. Now if the
Sir,
V0, yes,
110,
yes, 110,
110 divided by capital L into small l.
okay. So that means it is basically dividing the voltage with respect to the L. So L is the only variable. Here also L is a variable. Here also L is a variable. L we can vary physically in the rheostat, isn't it? So thereby actually what we are doing, we are changing the output voltage. So this is called the potential divider mode. So this is the difference between these two modes. Okay. Now you have understood. So what we'll do for this voltmeter calibration, as we are calibrating the voltmeter, we have to provide different voltage, and we have to see that what is the reading in the test voltmeter and what is the reading in the standard voltmeter. Then we can calculate the error for the test voltmeter, isn't it? And for ammeter calibration, we have to provide different current because ammeter reads the current. So current, how we can vary? Okay, so this is one arrangement by which we are varying the
Varying.
by varying the resistance, isn't it? Series resistance. By varying a series resistance, we can vary the current. Okay, but there is another arrangement we have for varying the current, which is called the load box. Can you recollect what is load box? Have you seen load box? Okay, so let me explain what is a load box. Now, what is a load? We many times we mention this word the load. Now, in electrical, we are specific significance for the load. What is load? Load for us is basically the current. Why it is current? Because load, by actual definition of load is that load is something which consumes the that electrical power. Load is something which consumes the electrical power. Now, how this power becomes the current? Now, you know that power is nothing but, for DC if we take, it is V into I. You all know this definition of power. V into I, voltage into current is the power. Now, if the voltage is constant, now if we vary the power, which will vary? The current will vary. So therefore, in our applications, most of the cases, the voltage doesn't vary because all the loads we connect in parallel. Like in your household, you have, what is the voltage of your household supply? Can anybody tell me?
220, so
220.
220 sets. 220.
Yes.
20, sir.
So these are the basic things that you have to remember. You may not be studying electrical engineering, but these are the very basic things that you have to remember. Okay. So 220 volt is the RMS voltage that we get as a single phase consumer. Okay. Now this 220 comes, there are two lines basically, one is phase, another is neutral. Phase and neutral, two lines come to our household supply. Okay, and how do we connect our load? We have a switch, then we have a load. Suppose it's a light load, is a light. So we have a switch, then we have a load. The next load, suppose the next load is a fan. So we have another switch. Next load, suppose we have a tube, a fluorescent lamp. In this way, all the loads are connected in parallel. All the loads are connected in parallel. Now suppose this lamp is 100-watt lamp. This fan is suppose 70-watt fan. This fluorescent lamp suppose 45-watt fluorescent lamp, including the ballast. So suppose if there is no load is connected or no switch is on, then what will be the current through this path? Can anybody tell me that what will be the current? Current is 0, isn't it? Now once we'll switch on one switch, so this is switch number 1, this is 2, this is 3. In this way we are connecting the switch. Now whenever we'll switch on 1, we'll close the switch 1. What will be the current? Can anybody tell me what will be the value of I?
Point
100 by
2.28
20 power by
Yes.
voltage.
So this is 100 by, sorry, is 100 by 220.
220.
So this much amps, this current will flow. What is that? Around 0.45. তাই না? কাছাকাছি একটা কিছু। Okay. Now when we'll switch on the, when we close the two switches, that means 1 plus 2, what will be the current? What will be the current? Current will be 100 plus 70 divided by 220. Okay, or you can separately calculate what is the value of 70 by 220. Isn't it? So in this way, actually, when we are increasing the load, we are switching on the load, then what actually changing? That change, that the variable which is actually changing is the current. So therefore, for us, the current is considered as a load. Okay. Now actually we have a load box made by ourselves, is available in our machine lab. I think you have seen these load boxes. Okay, and it has several switches. Several switches we have that load box. So this is suppose 1 ampere, this is 2 ampere, this is 2 ampere, this is 5 ampere, this is 5 ampere, this is 5 ampere. And we have two connecting terminals. Can you remember this box available
Yes, sir.
in
Yes,
our?
sir. Yes, sir.
Okay. Now, actually, what we connect the supply to this. And whenever we switch on this, actually, behind this 1 ampere switch, inside this box, there is a resistance. Whenever we'll switch on this 1 ampere switch, we'll close this 1 ampere switch. Exactly 1 ampere current will be drawn by that resistance. This is how discrete resistance are there inside the load box. And all these resistances are connected in series with a switch. And that switch you can see. And this series combination of this resistance and this switch is connected across this parallel terminal. Suppose this is a B terminal. This is A and this is B. So how they are connected? How these resistances are connected? The resistances are connected like this. Suppose this is your AB terminal. You have a switch and resistance. You have a switch and resistance. Okay, so this is how the load box is made. So this is A and this is B terminal. And this switch you can see out from outside. This is 1, this is 2 ampere like this. Have you understood what is load box? So that means load box is basically combination of parallelly connected resistances. Okay. So that means whenever we are mentioning that we have to provide the current for calibrating ammeters. And we have shown the resistance over here. So this R1 resistance is basically that resistance which is available inside the load box. Because by that resistance you can increase or decrease the value of resistance in a discrete way. So therefore here we'll call this R1 as a coarse control element. Coarse control, not a fine one, because whenever you are connecting 1 ampere, so whenever you are connecting 2 ampere, you are changing the resistance discretely. There is a discrete jump in the resistance value. But using the variable resistance mode of rheostat, you can control the resistance much finer way. So therefore that control is called the fine control of resistance. So therefore there are two resistances given in the circuit when we are calibrating the ammeter. Now these are the instruments which we need to calibrate the ammeter and voltmeter. The first one will calibrate the ammeter. Now for ammeter, what are the ammeters you need? You need 0 to 2.5 and 5 ampere. Most of the ammeters have two ranges. Okay. And the second one is 0 to 5 and 10 amperes. And as I mentioned that we need a load box for coarse control of resistance and a rheostat for variable fine control of the resistance. For voltmeter calibration, you need two voltmeters, one for test, another for standard, and the rheostat. You need to change the voltage because here the rheostat will be used as a potential divider. So these are the instruments you need to carry out the experiment. Now the steps of the experiment are also given, but it will be better to show these steps by the video. So let me stop this share and go for the video. Can you see the video?
Laboratory demonstration for calibration of ammeter and voltmeter.
Can you see the video, everyone?
Yes, sir. We can.
Yes, sir.
Sound is
Yes, sir.
coming?
Yes, sir. Clear.
Okay.
Now let us connect these components for calibration of ammeter and voltmeter. First, let us have a look at the instruments for this experiment. This is a DC ammeter of range 0 to 2.5 or 5 ampere, and the next one is another DC ammeter of range 0 to 5 ampere or 10 ampere.
Okay, so here you can see that the smaller range will use for this test ammeter, that means this 2.5 and 5 ampere range will used for the test ammeter, and the larger range will use for the standard one.
Range 0 to 2. Next one is another DC ammeter of range 0 to 5 ampere or 10 ampere. The next component is the rheostat, which has 3 terminals, 2 of them called fixed terminals and the third one is the variable terminal. Its range is 100 ohm and current rating is 5 ampere. Next, 2 voltmeters, one with range 0 to 75 volts DC and the next one is 0 to 150 volt DC. We also use a load box of rating 0 to 20 amps in steps of 1 ampere and of voltage rating 110 volts. Usually this type of thick wires are used for connecting ammeters and this type of thin wires are used for connecting voltmeters. Experiment for calibration of ammeter. Let us connect the ammeters first as shown in this demonstration. The first ammeter is to be connected across these two terminals as shown and the second ammeter is to be connected across another two terminals as shown. So we have connected this ammeter of range 0 to 2.5 ampere as test ammeter and the next one of range 0 to 5 ampere as standard ammeter. For fine variation of current, a rheostat should be connected. First, the variable terminal is to be connected and thereafter the fixed terminal as shown. Now let us connect the load box across the terminals as shown for coarse variation of the current. Now the power supply is to be given to the circuit from the main supply board using the wires as shown. As seen, the supply is 110 volt DC. Putting on this switch, let us give power supply to the circuit. First of all, before taking the readings, we must check for the zero error of the ammeters if any. Now for coarse variation of current, let us use the load box. Now we shall use the rheostat for fine variation of current. Now using the rheostat, let us fix the current of test ammeter, say at 0.6 ampere. The corresponding reading of the standard ammeter should be noted. To cover the entire range of the test ammeter, we must use both load box and the rheostat. In a similar way, by varying the rheostat, we can set another current at the test ammeter and the corresponding reading can again be noted from standard ammeter. Thus, by using rheostat and the load box, when the entire range of the test ammeter is covered, then the experimentation is completed. Calibration of voltmeter. In this experiment, we should use these instruments. This is a DC voltmeter of range 0 to 75, and next one is the voltmeter 0 to 150 volt DC, and this is the rheostat of 100 ohm and 5 ampere rating. The rheostat will be connected as a potential divider. The rheostat has two fixed terminals. This is the one fixed terminal and this is the other. They are to be connected across these two terminals. This terminal, which is the variable terminal, is to be connected at this terminal as shown. Now let us connect the voltmeters as shown here. This is the first voltmeter to be connected. Hence, this voltmeter is connected in the range of 0 to 75 volt DC across these two terminals, and this is the second one, and the second voltmeter is connected in the range of 0 to 150 volt DC across these two terminals. These two terminals should be shorted to complete the circuit. Thus, the circuit connection is completed for calibration of voltmeter. The supply is given similar to the previous experimentation for calibration of ammeter. calibration of ammeter, first of all we must check for the zero error for both the voltmeters. If any, that should be corrected first. The moving contact of the rheostat is to be varied to vary the voltage across the voltmeters. Thus, by varying the rheostat, let us set the voltage across the test voltmeter at a particular value, say at 10 volts. The corresponding reading of the standard voltmeter should be noted. In a similar way, by varying the rheostat, we can cover the entire range of the test voltmeter, and at different readings of the test voltmeter, the corresponding readings of the standard voltmeter should be noted. Thus, the experimentation is completed for calibration of voltmeter.
Okay, so this is the complete video we have for this procedural part. Next, we'll go back to the report part. So this is the run one where we do the ammeter calibration, and in run two we have the voltmeter calibration. So in ammeter calibration, as we have seen, generally the test ammeter has less range compared to the standard ammeter. And what we do, suppose if we want to calibrate 1 to 5 ampere, so for each discrete ammeter reading, first we'll set that ammeter reading at the test ammeter, then we'll check how much we are getting from the standard one, then we calculate the error. Okay, so therefore in the table also we have the test ammeter reading in the first column, because that is the independent variable here. So the test ammeter reading will be in the first column, then the standard ammeter reading. Then we'll calculate the error like this: the test minus standard. So that is the error. Okay, error can be negative, error can be positive. And the full scale percent full scale error is calculated like this. That is the error, actual error, divided by the full scale reading of the test ammeter. If the test ammeter range is 5, so we have to divide it by 5. For all this discrete reading, we have to divide it by 5 only. So this is how we can determine the percent full scale error. Similarly, for voltmeter also, we can calculate the actual error and the percent full scale error. And this is the report part. So that's all for this experiment. If you have any query, you can ask. If you have any question. Don't have any question? Okay. If you have any question, you can directly talk to me, unmuting yourself. Don't need to write anything in the chat. Okay. I'm stopping the share. The next experiment which we have, that is the starting and speed control of DC shunt motor. Okay. Now for this, I think you almost forgot things about the DC motor, isn't it? Can you remember anything about the DC motor, DC machine? Because all those are there in your syllabus of basic electrical engineering.
So only that it converts like the electrical energy into mechanical energy.
Okay, so any motor converts electrical energy to mechanical energy. Okay, but I think you haven't forgot the Fleming's rules, left hand rule and right hand rule. Okay. Uh,
No, sir. Yeah, we know.
don't remember?
No, we remember.
You can remember that.
Yes, sir. The left hand rule, like there was the thumb was towards what to say, towards a motion. The for
Mhm.
index finger was towards the field, and like the middle finger was towards the current. It gave us a direction of current. It was a Fleming's left hand rule, if I'm not.
Okay, nice. So where we use this Fleming rules, left hand rule, right hand rule?
So like in the left hand rule, we can what to say? We can find the direction of the motion, like when we know the current direction and the magnetic field direction, we can easily find the direction of motion from the left hand.
Okay, so here I have defined this electrical machine. An electrical machine is an electromechanical device in which either electrical energy is converted to mechanical energy or vice versa. So the machine in which the electrical energy is converted to mechanical energy is called the motor, and the reverse one, that means the machine in which the mechanical energy is converted to the electrical energy, is called the generator. This we all know, I think we should know. Okay, but this conversion should take place in the presence of magnetic field only. So that is the most important point. If this conversion takes place in the presence of any other field, then we should not call it a motor. So this conversion should take place in the
So,
presence
so
of
can
magnetic
you
field.
repeat? Can you repeat this part again?
So I'm just explaining whatever I have written on the slide. I just told that the machine in which the electrical energy is converted to mechanical energy is called the motor, and the machine in which the mechanical energy is converted to electrical energy is called the generator. But this conversion of energies should take place in the presence of magnetic field only. Then only we should call it as an electrical machine. Okay. Now, why we stretch the hand like this? Because this is the easiest way by which we can create three axes of a Cartesian coordinate system, which represents the 3D. You can't make it by any other finger combinations. By only this three finger combination, you can make a three-dimensional coordinate system very easily. So therefore, we stretch the fingers like this. Okay. Now here I have shown two basic principles which we study in our school days, maybe in 7th or 8th standard. Okay, now this is very powerful. I should say is a very powerful principle by which we can explain any principle of electrical machine. Okay, now whenever we'll stretch these three fingers of our hand, the representation doesn't change if we go for left or right or left. The representation doesn't change. That means always this thumbs represent some mechanical quantity, thrust or motion. Always this index finger represents the magnetic field, and always the middle finger represents the electrical quantity, maybe current or voltage. Okay, so you should not forget this rule by which we can explain any machine. Anyway, so machine can be different types of machine we have, like AC, DC, radial flux. So I'm not going into the details. We have only the DC motor. This is very specific motor, DC motor, which is generally used for the nowadays, which is used for your toy cars, which is used for electric trains, which is used for trams, metros, which is used for e-vehicles, electric vehicles, and which is used for most of the cases where we cannot connect our alternating supply. We have to give the supply by the battery source. So everywhere we have to use the DC motor only. Okay, so this is very popular motor, we can say. Anyway, so that DC motor, there are different types of DC motor. Now we have depending on the type of connections, the field connection, as you know that DC machine can have mostly four terminals. One is the armature terminal, two armature terminals, and two field terminals. Okay, so two armature terminals and two field terminals. Now, what is armature? I understood that you just forgot all these terms, armature fields, isn't it? Can you recollect these terms, armature and field? Nobody. Okay. So armature is basically that part of the machine which represents the middle finger of this Fleming's rule. So that means which represents the current carrying conductor. Armature is that part of the machine which represents the current carrying conductor. And field represents that part of the machine which represents the index finger. That means which is responsible for producing the magnetic field inside the machine. So that is the difference. Now you will say that why we need the coil for the field, because we have to provide a magnetic field inside the machine. So magnetic field can be easily produced by some permanent magnet. That's right. Permanent magnet can also be used. And if the permanent magnet is used inside the machine, we don't need any coil. Okay, but in most of the machines available in the market, we have electromagnet, not permanent magnet. And how we can create an electromagnet? An electromagnet can be produced by a coil is wound on a iron core. Okay, so that coil is called the field coil. Have you understood? So that is the field coil. And the armature coil is the actual coil which is responsible for carrying the actual current of the machine. Field coil is only produce the magnetic field which is required for this energy conversion, as I mentioned. By definition, the energy conversion should take place in the presence of a magnetic field. Is that clear? Okay, so have you understood this term? I am not getting any answer. Are you sleeping? Or you
Yes,
just
sir.
logged in and
Yes, sir. We are understanding this thing.
okay. So I am not going I am not just teaching you very tough things. Only in some lucid terms I uh, trying to explain the things. Okay, so everything you can explain from the Fleming's rule, Fleming's left-hand rule. So here, as I told you, that armature is basically representing the middle finger in the Fleming rule, and the field is representing the index finger. And if we provide these two, then only we'll get some mechanical motion, mechanical force, mechanical torque. Okay, so that's the thing. Now, when we'll give some supply, because through this armature we want to flow some current, otherwise how the motor will rotate, how the motor will generate the torque. So we have to apply some voltage across the armature. What about the field? As it is an electromagnet, that field coil also should be excited. Field coil also should have some current through it. Okay, so we can arrange the current through the field by some external DC voltage, or we can give the same DC voltage that we have given across the armature. Okay, so if we do like this, the same voltage source which we have excited the armature, if we excite the field coil by the same voltage source, it is called the shunt, because it is kind of parallel thing. So shunt means parallel. Okay, so therefore it is a shunt motor. We can call it a shunt motor. If the configuration is this, and if the motor starts rotating, then it's called the shunt motor. Okay, but shunt motor should not be connected directly across the supply to start the motor, because there is a certain disadvantages of that, certain problem of that. So generally what we use, we connect some starter through this supply, and the starter is connected with the motor. So that is called the shunt motor starter. So there are two types of starter, 3-point starter and 4-point starter. So you can remember this term, 4-point starter. Okay, so what I told, that the shunt motor should not be started direct online. So that means directly by switching the supply, the shunt motor should not be started. The shunt motor should be started by some starter only. Now, the most popular starter is called the 4-point starter. I will show that what is 4-point starter. Okay, so that is one part of the experiment. How we will start a DC shunt motor by a 4-point starter. So that is a part of the experiment. And then the next part is how we will control the speed of the DC motor, DC shunt motor. Okay, so there are two ways of controlling the DC shunt motor speed. The two ways are, first one is field flux control. Field flux control, and the second one is armature control. Now you have understood this term, what is field and what is armature. So that means in one part we'll control the field current, in another part we'll control the armature voltage. So field flux means nothing but the field current. You can also call it field current control. And armature voltage control means you have to connect some rheostat. By that you have to control the armature voltage. It's very easy. Okay. Now we'll stop this share and we'll share the actual circuit diagram. Just a minute. Can you see this? So this diagram I have already shown you. So how the shunt motor is connected with the supply, the armature and the field, they are connected in parallel in shunt, and then they are connected with the DC supply. Okay. Now where we have the,
So where is the stutter?
I will show that.
Sir, can you repeat the starter part?
Which one?
Starter part.
Starter part. Starter or stator? Stator
Yes,
is
sir.
different and starter is different. Starter only to start the motor. Because if we directly switch on the DC motor, okay, so then there may be some problem. So to avoid this problem, we generally connect a starter with the DC motor, then we'll start it.
Sir, which kind of problems
What kind
if
of problem you
we
are asking?
do not use any starter?
What
Yes,
kind
sir.
of problem you are saying? Okay, so the problem is, if you connect, actually what happens? Actually, I'm not going into that details, but if you ask me, then I can explain that. Now, in DC motor or in any DC machine, there is a voltage induced voltage. Now, for generator, it is called the induced voltage, but for motor, it is called the back EMF. The expression is same. Okay, it is proportional to speed. It is proportional to speed and flux. Now, when the DC motor is not started yet, what is the speed? Speed is 0. If the speed is 0, what is the value of back EMF? Back EMF is also 0, isn't it? Now, the basic equation for any DC
Zero.
machine is Vt equals to Eb plus IaRa. Now, how the current can be calculated? Current is Vt minus Eb by Ra. Now, if Eb is 0, then the current will be just Vt by Ra, which is very high value. The current will be very high. Okay. That means if we directly connect the Vt to the DC motor, the current will be quite high compared to its rated current, which is given in the nameplate. Okay. Have you understood?
Yes, sir.
Now what we can do? This Vt by Ra, this is the current, starting current, isn't it? This starting current we have to reduce. So how we can reduce the current? There are two ways, either by increasing the resistance or by decreasing the terminal voltage. মানে শুরুতে আমি ভোল্টেজটা কম দিতে পারি বা শুরুতে রেজিস্ট্যান্সটা হাই রাখতে পারি, এইভাবে কারেন্টটাকে কমাতে পারি। তো in this is 4-point starter, what we do, we increase the resistance initially. We keep a very high resistance in series of the armature so that the current flows through the armature is less. Then gradually we reduce the resistance, because ultimately ওই রেজিস্ট্যান্সটা যদি রেখে দিই in the circuit, then it will be a huge voltage drop and unnecessary power loss. So we cannot keep the resistance in the armature circuit. So we have to remove it from the armature circuit once the motor is started. Once the motor is gaining the sufficient speed, when the sufficient back EMF is already developed, we have to reduce the resistance. We have to remove the resistance from the armature circuit. Clear?
Yes, sir.
Okay. So that is why we use the DC shunt motor starter. Okay. Now I want to share the actually that instruction sheet. Do you have the instruction sheets for all these experiments?
So no, we don't have.
You don't have, isn't it? Okay. So let me check whether I have. Tomorrow, yesterday, Arindam sir didn't share you that, because I have already sent him.
So no, like he told that he will share those things, but yet like we haven't received any mail from his side.
Okay, so let me check. Just wait some minute. I'm just checking whether I have the instruction sheet, because I thought that he might have sent you the instruction sheet. Starting and speed control of the DC shunt motor. So can you see now?
Yes, sir, it's visible.
Okay, so this is the circuit diagram for the experiment. Starting and speed control of DC shunt motor. Okay, so here you can see that there are two coils. One is called armature coil. It has two terminals, A1 and A2. And another coil is called the field coil. It has a terminal of F1 and F2. Now, our objective is to connect these two coils with the supply properly, so that without any problem, we can run the machine successfully. So that is our objective. Now, how this armature coil and field coils are connected to the supply, that is given in the figure. Now, as I told you, so due to avoid the starting problem, we generally use 4-point starter. Now, in the figure, you can see the 4 points. What are the 4 points? L1, L2, A, and F. So therefore, it is called the 4-point starter. It has 4 terminals rather. And terminals are named as L1, L2, A, and F. These are the 4 terminals. Now this L1 and L2 will be directly connected with the source, voltage source, or the supply voltage. Now A will be connected with the armature, F will be connected with the field. So therefore the names are A and F. Now here we are not directly connecting A with the armature because we have another part of the experiment that is called the field, that control of speed. So therefore what we are doing, we are connecting the A terminal to the armature via a rheostat and an ammeter. Are you getting? Okay, we might
Sir,
connect
repeat
the
once.
armature directly to armature, this A terminal directly to the armature, but we are not doing that because in the second part of the experiment, we have a speed control. So there we need some rheostat, which will be connected in series with the armature. এই জন্য আগে থেকেই আমরা একটা সিরিজে রিওস্ট্যাট আর অ্যামিটার কানেক্ট করে তারপর আর্মেচারটাকে কানেক্ট করছি। হ্যাঁ বলো কি বলছিলে? Somebody was asking something.
Sir, I was asking, please repeat this part one.
হ্যাঁ
স্যার একবার রিপিট করবেন, এই জায়গাটা বুঝলাম না ঠিক।
হ্যাঁ আমি তো সেটাই বলছি যে that starter has 4 terminals. Now L1, L2 are the line terminals. Line terminals means where you will connect your supply voltage. And A and F terminals of the starter. The A should be connected with the armature, F should be connected with the field. As I already told you that always there will be 2 coils in any machine. In any DC machine, there will be 2 coils, one field coil and the armature coil. Now this A terminal of the starter should be connected directly with armature and F terminal should be connected with field coil of the machine. Now we are not directly connecting A with the armature because in the second part of the experiment we have to control the speed of the DC motor. So therefore the arrangement we are making beforehand. আগে থেকেই আমরা অ্যারেঞ্জমেন্টটা করে রাখছি। সেটা কি না একটা সিরিজের রিওস্ট্যাট আর একটা অ্যামমিটার, এই দুটো সিরিজের থ্রু দিয়ে তারপর অ্যামমিটার এই এ টার্মিনালটা আর্মেচারের সাথে কানেক্ট করছি। Similarly, the thing we are doing for F terminal. F terminal also we can connect with the field directly, but we are not doing that. We are connecting F to the field via a rheostat and an ammeter. Okay. So this is the main part of the circuit. At the end, what we are doing, we are connecting the other terminals because both the armature and field coils have two terminals. দুটো করে টার্মিনাল আছে, একটার সাথে তো আমি ওটা করলাম, বাকি যে টার্মিনাল দুটো পড়ে রয়েছে Rest of the terminals which are left, F2 and A2, they will be shorted, and the shorted terminal will be returned back to the supply L1. So that is the complete connection for this particular circuit. And at the end, you have to connect a voltmeter. So that is the last part of the circuit, because voltmeter is not an essential part of any circuit. Without the voltmeter also, any circuit can work. But without ammeter, if ammeter is out of order, the circuit will not be completed. So ammeter is an essential part of the circuit, not the voltmeter. ভোল্টমিটারটা যদি খারাপও হয়, বড় জোর ওটা রিডিং দেখাবে না, কিন্তু সার্কিটটা কমপ্লিট থাকবে। সেই জন্য ভোল্টমিটার we should connect at the end. Okay, so have you understood this circuit? So then I will go for the procedure.
Yes, sir.
Okay,
Yes,
I'm
Got it.
stopping this share. Let us go for the procedure. Just a minute.
Starting and speed control of DC shunt motor. In this experiment, you will learn how to start a DC shunt motor by a 4-point starter and how to control the speed of the motor. Two types of speed control will be employed here. One is field flux control, another is armature voltage control. You will also see the effects of interchanging the supply terminals, the armature terminals, and the field terminals. First of all, you have to observe the DC shunt machine and its 4-point starter. The machine has 4 terminals, A1 and A2.
So as I mentioned that it has 4 terminals. 2 terminals are for the armature coils, that is A1 and A2, and 2 terminals for the field coils F1 and F2.
Two at the armature terminals, F1 and F2 at the field terminals. The 4-point starter has also 4 terminals, L1 and L2, A, F.
Okay.
The connection you have to make will include.
Can you hear the sound of the video?
Yes, sound is audible, sir.
Okay.
Starting and control features. From this live power panel, you have to bring this 110 volt DC supply to this experimental table, but that will be the last step. Suppose the supply is coming here. Now if you switch on this, then immediately you will get 110 volt DC over here. Connect these two terminals to L1, L2 terminals of the starter.
The supply will be connected with the L1, L2 terminals of the starter. So this is how he is connecting the supply to the L1, L2 terminals of the starter. But we haven't given the supply yet, because as per our procedure, we connect the supply at the end. And this is the
Connect
connection.
A terminals of the starter to A1 terminals of the motor through a rheostat and an ammeter in series.
So the A terminals of the starter will be connected with A1, but through rheostat and ammeter in series. So you just observe, we are taking a larger rheostat which is having more current rating and higher range of ammeter, because the armature current is always higher than the field current, because the armature coil is the main coil which carries the maximum current of a DC machine. So this is how he has connected armature, this ammeter and rheostat in series, and at the end the connection will be terminated at A1. So A part is complete. Then the same thing.
Similarly, connect F terminal of the starter to F1 terminal of the motor through a rheostat and an ammeter in series. As the armature carries the maximum current, the rheostat and ammeter connected in the armature circuit will be of higher rating, that is of 5 ampere current rating. But the field rheostat and ammeter will be of 1 ampere current rating. Now sort A2 and F2 terminals of the motor and return these two sorted terminals to L1.
The remaining two terminals of armature and field coil will be shorted, and the shorted terminal will be returned back to the supply terminal L1. This is the sorting is returning back to the L1 by this red wire. Now at the end,
Connect a voltmeter of
will be connected.
150 volt rating to A1 and A2 terminals to record the armature voltage. If all these connections are okay, you can connect the supply. Connect one end of two supply cables to the experimental board first, and then connect other ends to the light power panel. To start the motor,
Can you see the third part?
Yes, it's visible.
you have to switch on the supply first. Then pull the handle of the starter up very slowly and leave it at the extreme position. You see, the handle is staying at the extreme position. This is because of the attraction force of the holding coil. You see, the machine is running, but you have to observe that all the meters are giving positive reading. Here this ammeter is not giving positive reading. That means you have to reverse the terminals of the ammeter. Now you see, this is giving positive reading. To stop the motor, simply switch off the supply. The starter handle will go down automatically.
So this is how we can start a DC shunt motor by using a 4-point starter. The next part will be the control, speed control of DC shunt motor. First one will be the field flux control, and the second one will be the armature voltage control.
In the second run, you have to vary the field current by this rheostat, keeping the armature voltage constant at rated armature voltage, that is 100 volts. In the steps of 0.05 ampere, you have to increase the field current to its maximum value, and we have to record the speed from the tachometer. And the armature current from the ammeter. In the same steps, you have to reduce the field current, and then you have to take the same readings. In the third run, you have to vary the armature voltage, keeping the field current constant at its rated value. The rated field current means the field current which gives the rated armature voltage, that is 100 volts, and the rated speed, that is 1150 rpm of this particular machine. Now you see, we are getting the rated field current in this particular case 0.51 amps. Keeping this value constant, you have to reduce the armature voltage in steps of 10 volts by this rheostat up to 0 volt. Now in this run, you have to record the speed and the armature current just like the previous run. Leave the rheostat setting for 20 volts armature voltage so that the machine rotates very slowly and you can see the direction of rotation. Now switch off the supply. Interchange the supply terminals. Again switch on the supply. Run the motor by the starter. Observe the direction of rotation, whether it is being changed or not. Again switch off the supply. Interchange these armature terminals, that means A1 and A2. Switch on supply again and run the motor. Observe the direction of rotation. Now again switching off the supply, interchange the field terminals that is F1 and F2. Again switch on the supply and run the motor. Observe the direction of the rotation.
So that's all about the experiment. Now, have you observed that direction of rotation is changing with the reversal of supply terminals, armature terminals, and field terminals, where the direction of rotation is getting changed?
Yes, sir.
Getting changed or not? So that is one run actually. So you have run 1, run 2, run 3, and run 4. So in the run 4, you have that. So interchange the field terminals, observe the direction of rotation compared to the previous directions, and repeat for the armature terminals as well as for the supply terminals. So three combination you have to check. First, we have to check by interchanging the supply terminals. Then you have to check the direction of rotation interchanging the armature terminals, and then by interchanging the field terminals. You have to observe that in which change the direction of rotation changes. Because if we want to if you want to run the motor in reverse direction, suppose a tram is going a forward direction, sometimes a tram going backward direction. So what you have to change actually, that you should know. So how to run the motor in a reverse direction? If we change the supply terminal, whether we can change the direction of rotation. So that you should know. So therefore, this run is there. Have you observed this? You haven't observed, isn't it? Uh, Anybody tell me that what actually will happen by interchanging these terminals? Okay.
So
So
actually,
direction,
the video was choppy at that moment.
Hmm?
For supply terminals, the video was quite choppy at that moment.
so direction of flux changes.
Which one? For which combination? Which change? Supply terminals, armature terminals, or field terminals? There are three changes.
So supply term.
Supply terminals. Okay, you just look at this Fleming left-hand rule. Now, whenever we'll change the armature terminal, what will happen? The direction of the middle finger will change, keeping the other two fingers same.
Yes, sir.
Okay. So what will be that? How we can do that? Keeping the magnetic field same, if you want to change the middle finger direction, so what will be the direction of rotation or motion or thrust? You just stretch your own fingers of left hand and check. Middle ফিঙ্গারটাকে রিভার্স করো, ম্যাগনেটিক ফিল্ডটাকে সেম রেখে, দ্যাট মিন্স ইন্ডেক্স ফিঙ্গারটাকে সেম রেখে দেখো থাম্ব ডিরেকশনটা চেঞ্জ কোন দিকে হচ্ছে বা হচ্ছে কিনা আদৌ।
ডাউনওয়ার্ড হবে তো।
মানে রিভার্স হচ্ছে, তাই তো?
হ্যাঁ, রিভার্স হচ্ছে।
রিভার্স হচ্ছে। এবার উল্টোটা, মানে আমি যদি আর্মেচার টার্মিনালটাকে ফিক্সড রেখে ম্যাগনেটিক ফিল্ডটাকে উল্টাই, মানে হচ্ছে ইন্ডেক্স ফিঙ্গারটাকে উল্টাই, মানে হচ্ছে ফিল্ড টার্মিনালটাকে উল্টাই, তাহলে কি হবে? Keeping the middle finger same, you just change the field terminals or the magnetic field. what will happen?
তাহলেও স্যার রিভার্স হচ্ছে।
তাহলে reverse হচ্ছে। That means by changing the armature terminals or by changing the field terminals, we can reverse the direction of rotation. But if we change the both, then what will happen? Check. দুটোই চেঞ্জ করে দিই।
দুটোই চেঞ্জ করে সেমই থাকবে।
দুটো চেঞ্জ করলে
Reverse
সেম
তো-
থাকছে। Okay.
Hmm.
So that means let me now go back to the whiteboard. Okay. So we have that. Okay. Now suppose when we have supply terminals like this, current is entering from this side and this side, because that side is positive, this side is negative. Okay, so this gives a certain direction of middle finger and index finger, isn't it? Okay, and suppose the direction of rotation is like this. Now whenever I will change the supply polarity, the current will enter from this and this. So that means both the armature current and field current reverses. That means both the middle finger and the index finger reverses, changes their direction. So that means the direction of rotation will remain same. So that means the supply polarity reversal doesn't have any role in changing the direction reversal of a DC shunt motor. Have you understood this point?
Yes, sir. Now I've got it.
Okay, that's fine. So that is the thing. So one more thing I should point out here, that so that fourth run you have understood, the first run you have understood, the starting part and the direction reversal part you have understood, but the field control you haven't understood, I know, because you don't know the theory, or you might have forgot all the theory, isn't it? Okay, একটু জাস্ট বলি, না হলে এটা কমপ্লিটই থাকবে। Okay, so as I told you that EB is a phi and omega, isn't it? Now, can you recollect the Fleming's rule? So suppose we have a generator. What we need for a generator? What are the input thing? জেনারেটরের জন্য আমাদের কি কি ইনপুট দিতে হবে? We have to give some mechanical rotation and we have to provide some magnetic field. Then only we'll get the voltage. So this we can say that right hand rule. Okay. Similarly, left hand rule also we can write like this. Suppose in a left hand rule, what will provide? Will provide the flux, because flux is everywhere. Magnetic field you have to provide in any machine, irrespective of it is generator or motor. And what are the things you have to provide? You have to provide a current. And when you provide these two, then only you will get the mechanical thing, that is the torque. Okay, so these two are the very important relation for electrical machines. For any electrical machine, these are two very important relations. How to generate the voltage and how to generate the torque. Now, this you can remember very easily by the Fleming left hand rule and right hand rule, isn't it? Because you know that there are three fingers. So this is always your thumb. This is the index finger. And this is the middle finger. So if we provide these two, you will get the voltage generated for a generator. And this is the left hand rule. Okay. Now as far as the speed is concerned, so as you can see that EB equals to K phi omega. Now from this expression, is the very basic expression of DC machine, what you can write about EB? EB you can write from that expression is Vt minus IARA. Now that means if we equate these two, EB, so you will get Vt minus IARA equals to K phi omega. So this is how you can understand how you will change the speed. So omega is basically Vt minus IARA by K phi, some constant into flux. Now you just tell me that by changing the field flux, how we can change the speed. Suppose if we want to, if we change the, if we increase the field flux, what will happen? Or if we decrease the field flux, what will happen? Keeping
So
other thing
inversely
constant.
proportional.
Huh? Inversely proportional,
Inversely
isn't it?
proportional.
So that means if we reduce the flux, we can increase the speed. If you reduce the flux, we can increase the speed. Okay, so that means the field flux control to get the increase in speed. And what about the armature voltage control? Okay, so if we change the resistance, what will happen? If we change the resistance, armature resistance, what will happen? What about the speed? It will decrease or increase. Suppose we are increasing this resistance. What will happen?
It will decrease, sir.
The speed will decrease because that is in negative sign, isn't it? So that's all. So this is how we can control the speed. In the first, in the second run, we are controlling the flux. Actually, we are reducing the flux in the second run. And in the third run, we are increasing the resistance. By increasing the resistance, we can reduce the speed. By reducing the flux, we can increase the speed. So you can remember this relation only. So Vt minus IARA by Ka phi. That's all. Okay, so that's all for now. So if you have any question, you can ask.
Sir,
Yes.
in the previous experiment, equal writing point number 4, that plotting part. Can you tell that plotting part?
Actually, for plotting, you need the data. But right now you don't have the data because physically you are not coming to the lab. So, so that I don't know. Other teachers are. Have they told you something regarding the report part?
No, like they only discussed what we would have done in the report.
Yes, yes. Okay,
Since
that's all.
we
So that's all
don't have to
only.
do the report
How
thing.
to actually perform the experiment in lab? What is the theory and what is the procedure and how to relate the theory with the experimental thing. So that's all. That only we can do right now in the virtual mode, isn't it? Because the report part, for report part, you need the data. You have to come to the lab. You have to do the experiment by your hand. Then only you can collect the data. So anyway, if you have any more question, do you have any more question?